Hello everyone, we're Group 13, and we're glad to introduce you our design improvement on the robotic spine. Understanding the human body has become a central goal of many research programs over the past decades. The spine is one of the major components of human body, since the spine is important in supporting the human body and maintaining stability. Today, more than 80% of the world population is suffering from disease associated with spine, such as lower back pain. Although extensive studies have been carried out on human and animal cadavers, little is known about the response of the spine to the complex dynamic loads in vivo. Therefore, to better understand the human spine, a biomimetic robot that models human spine and the surrounding tissues is developed. Professor Driscoll's lab has been developing a biomimetic robotic spine for a long time. The current model is called TIM, which means testing of inflated muscles. As shown in the picture, the inflated muscle and the controlling system are completed. However, the discs of the current model are made by some hard polymers, which is not capable of modeling the behavior of human IVDs. Therefore, the spine becomes overstiff and cannot move flexibly. In this situation, a better design of human IVDs, which is our design, is accomplished. Our team aims at designing a biomimetic artificial IVD that can model the dynamic response of human IVDs and a sensing system that can measure the response pressure. To obtain a good artificial IVD, there are three critical requests that must be met. First, the IVD has non-homogeneous mechanical properties. A lot of current IVD designs are using homogeneous material. However, human IVD has significant non-homogeneity in different sections. Second, the human IVD has nonlinear elastic modulus under compression and tension. Third, as people in different gender and age groups would have very different IVD properties, large uncertainty will be introduced in our design. To measure the response pressure, the sensing system must be calibrated and integrated. With our objectives identified, we generated 4 design concepts and selected the best one based on the need of our client. The artificial IVD consists of 6 sections made from 4 different materials, so that our design would have different mechanical property in different sections and a nonlinear modulus on the compression and tension. Now the problem is, how can we figure out each of the 4 materials that we want to use? We adopted a data-based computational optimization process and performed reverse engineering design. After collecting the experimental data from sample IVDs donated by people in different ages and genders, we assign different weight to each data point based on the Canadian population proportion. Then we numerically optimize the property of each material so that the overall modulus of our design is the closest possible to actual human IVDs. After obtaining the elastic modulus of the materials, we use FEA to calculate the overall tensile and compressive modulus of our IVD and then compare the result with the experimental data. As you can see from this figure, the overall tensile and the compressive modulus falls in the error box of the experimental data, which indicates that our design can model the mechanical property of the human IVD very well. Using the optimized elastic modulus, we selected 4 materials and manufactured the prototype via casting. The picture on the left is the prototype of the artificial IVD. Not only did we make a prototype of the artificial IVD, but we also integrated the artificial IVD and our sensing system to the actual model. These 2 videos on the right shows the behavior of the model and the IVD pressure measurement when the spine was bended. With the working prototype, we successfully measured the pressure change of each IVD in the lumbar region. These curves describe how the pressure in each IVD changes with the increase of the bending angle, where the bending angle is defined by the angle between the vertical direction and the line connecting the head and caudal vertebra. Future experiments will be done after the artificial muscles and the artificial thoracolumbar fascia are installed. The experimental result measured from the robotic spine will be compared to that of human spine, which can generate an inner view of human spine dynamics. Consequently, this result will contribute to the treatment and precaution for spine-related disease. Thank you so much for watching. We are looking forward to meeting you in the design day, and more details will be given during the exhibition.